This is Akashvani. Titled Mathemagic, the Theory of Curiosity. Participating in the interview is Dr. Anup Dixit, Assistant Professor, the Institute of Mathematical Science, Chennai. Mathematics is often viewed as a complex subject, but it can also be a source of fascination and fun. There are probably many numbers and numerical concepts waiting to be discovered. Let us enjoy the fascinating world of mathematics and numbers and discover how they can be a rich source of entertainment and enjoyment. Hello, Dr. Dixit. We're very happy to have you in our studios at Akashvani.
Hi, nice to meet you.
To begin with, this is the basic question everybody gets. Like, for those who are outside academia, when we think of mathematics, why is it like we only think it's only numbers, calculations? How is it for a mathematician like you? Do you think it is beyond all that?
See, mathematics is a subject which is born out of pure human curiosity. Now, in early days, it helped people perform some basic operations such as counting cattle, keeping track of lunar and solar calendars, the barter system, etc. But in general, if you want to describe a mathematics, then it follows the following steps. First is we have certain rules which are also called axioms in mathematics. And using those rules, there are certain statements that you can very easily deduce. I'll give you one example. In Euclidean geometry, if you consider a triangle and saying that the length of two sides are the same is the same as saying the two interior angles are the same. So it means it's an isosceles triangle. So this is a statement which is quite easy to see. But then again, in Euclidean geometry, you can come up with a statement such as if you take a right angle triangle where one angle is 90 degrees, then the sum of the squares of the two shorter sides is equal to the square of the longer side, which is the famous Pythagoras theorem. Yeah. All of us learn it in our middle school or high school, but it's a beautiful statement. So just remove all the knowledge of Euclidean geometry from your mind, you come across this statement, it's beautiful. It's not too difficult to prove, all of us would have seen a proof in our lifetime, but this is a glimpse of what mathematics is all about. So right now there are several sub-disciplines in mathematics such as algebra, analysis, topology, number theory, probability theory, etc., etc. But all of them follow the same principle. We have certain rules which we call axioms. And using those rules, you can keep introspecting and going deeper and deeper, and then you come up with statements which are not at all obvious and which are true nevertheless. And that's what we are after, truths or theorems. That's
Yeah, so that was very nice. Why do you think there is a disinterest among young children or young adults when it comes to mathematics?
So usually the disinterest among students arise when they are not introduced to the topics in the correct way. So this results in sometimes students doing really well in mathematics or the things that they see, or sometimes they're not being able to do it and they conclude that they are not good at it.
Right.
But so I'm not saying that mathematics is easy. It is difficult, but it is also really interesting and it has an aesthetic appeal to it. So often there is a comparison made between mathematics and music, and I agree with it. So music is not easy and not everybody has to like all different kinds of music. But there will always be some music that you really like and enjoy. And if you spend enough time, perhaps you can also compose. Mathematics is very similar. I'm sure there will be some type of mathematics that you will really enjoy if you learn it properly. And then to answer your second question on what we can do to make students appreciate the beauty of mathematics. So one way that I can think of is that for all the students, we have to somehow give them the experience of the joy of discovering mathematics. So somehow you need to create a scenario where the students themselves construct the building blocks towards arriving at a formula themselves or arriving at a theorem themselves. And once they are able to do it, I can tell you with full certainty that the joy of discovery is supreme. I mean, then they will get addicted to it. And another thing one can think of is personalizing mathematics to a certain extent. You can inspire students with stories of mathematicians, with anecdotes, giving them puzzles to solve. And that's definitely a way to get them interested. But certainly if you want them to get going, They need to experience the joy of discovering something by themselves.
True.
That's the...
Yeah, running with the syllabus, finding the previous question papers, how it was solved, that is again another problem. Okay. So when we look at the history of mathematics, like how it has evolved and other things, we cannot deny the role of India. So how do you see it in the Indian context, sir?
Yes, so again, mathematics has been born out of human necessity. If you look at different ancient civilizations such as Mesopotamians, Chinese, even ancient India, so the basic seeds of mathematical ideas, they started germinating more or less independently. But among us, if you ask me what one of the oldest serious mathematical texts that I will say is still Euclid's Elements, which one can trace back to 300 BC, which also follows a very modern approach. There are postulates and there are propositions. Certainly, India's contribution to mathematics has been immense. The notion of zero and infinity, which are such cornerstone ideas or mathematical ideas, they were discovered in ancient India. And also, if one goes as long back as, let's say, 800 to 1000 BC, then there were sutras highlighting interesting mathematical identities. For instance, the famous Baudhayana Sulba Sutra, it has a statement of Pythagoras' theorem in form of a verse, and along with several examples of Pythagorean triplets. A better documented era of Indian mathematics would be between, let's say, 400 to 1300 AD. And we had these mathematical maestros such as Aryabhata, Barahamira, Brahmagupta, Bhaskara, etc., etc. And in the later stage, we had the Kerala School of Mathematics. It got a lot of prominence during 1400 to 1600 AD. And to highlight some of their discoveries, they discovered mathematical induction. Then there's this famous Madhava's formula for pi, which he deduced by obtaining the Taylor expansion of tan inverse x, which is pretty phenomenal for that time. And if you fast forward then to 20th century, then of course we have Srinivasa Ramanujan, who is the most celebrated figure in Indian mathematics. But post Ramanujan, there have been several really illustrious mathematicians such as Ananda Rao, who went to Cambridge right after Srinivasa Ramanujan. Then we have S.S. Pillai, we have Vijay Raghavan, we have Sarvadaman Chawla, Harish Chandra. Just to name a few, there have been several people who have contributed a lot to global mathematics. So India has had its share of contribution. Certainly.
Okay. So just that you spoke about the celebrated and the legendary Srinivasa Ramanujan, sir. So how has his works, do you think, still influence, the different fields or diverse fields like space science, physics? So how do you think the influence continues?
So Srinivasa Ramanujan is an extremely inspiring story, and it has been romanticized for decades. So he was, if you think about him, he was a highly intuitive mathematician. He could predict formulas, and many of which are still quite mysterious. So it's a fascinating story. But what sets him apart is that he had this knack of picking diamonds from heaps of stones. What I mean by that is that many of his formulas are starting points for very deep and fascinating mathematics.
Okay.
So new subjects were developed starting from Ramanujan's formulas, so which took several decades to be developed.
Right.
So amongst his major contributions, one can say one is the theory of modular forms, which essentially developed after Ramanujan's conjectures on tau functions. And there is another method which is called the circle method, which is also called Hardy-Littlewood circle method, which again essentially was developed the theory was developed using Ramanujan's work on partition functions. But one lesson that we can take from Ramanujan's life is he may have been gifted or he may have been a genius, but he worked really, really hard.
True.
So if you think about it, for all practical purposes, no one around him understood what he is creating, what he is doing. He still continued to do, he still kept on writing on the floor, he filled the floors with chalks, he kept going. That's absolutely incredible. That's one lesson that everybody should take from Ramanujan's life, is that there is no alternative to hard work.
True.
Now, coming to your second question on how has Ramanujan's work influenced science, on contemporary science, only recently people are recognizing his works on modular forms and mock modular forms, which is having influence on quantum field theory and string theory. So the concept of modular forms is basically to understand functions which have a lot of symmetries. Now, in supersymmetric quantum field theory, often counting certain states, such as BPS states, on manifolds of higher dimensions is important. Now, this counting function is precisely given by some mock modular forms. For instance, the BPS counting function in the 6-dimensional space-time torus is nothing but the inverse of Ramanujan delta function. So, if you ignore these jargon, then the point is that the work which was pioneered by Ramanujan about 100 years ago is still so influential in today's day and age, and that's something which is very typical of mathematics. In fact, even if you remember Einstein's general theory of relativity, the mathematical tools required to develop the theory was already existing 50 years ago, but it only took shape much later. So usually this is what happens. Mathematics is far ahead of the other sciences, and then once they need it, they use it when time comes.
True. Yeah. That's well said, sir. So now, off late, we've been talking so much about AI applications into our everyday lives and other things. So how do you think this mathematical concepts would help, coding? And do you also think AI will take over in future?
Yeah, that's an excellent question. AI is the buzzword these days.
Right.
So the mathematics behind artificial intelligence, it involves, the theoretical part involves basic linear algebra and calculus, which we teach in any BSc course in their first year. So that's the theoretical part. I'm not saying that it's all easy. Of course, the applications of linear algebra and calculus are quite sophisticated to develop an AI, but the theory part is pretty standard. Now, talking about AI, whether it will take over our jobs or not, we are still in a very early ages of AI. So the AI language model, such as the ChatGPT, has been very successful. But if you really think about it, ChatGPT is nothing but a glorified search algorithm. So we have all experienced, for example, Gmail's autocomplete predictions. Like you write something on an email and it will predict what's going to come next even before you have written it. So the reason it's able to do it is because it has access to a lot of human texts and it can recognize patterns. And ChatGPT does the same thing, but it can do that to sentences and paragraphs altogether. So then, and the way it does it is it has access to trillions and trillions of texts in the world. But this is not, I'm putting it in a very naive way. It is also learning from whatever it's doing. But having said that, it is still some kind of a glorified search algorithm, and going through these trillions and trillions of text, it takes a lot of energy to run these programs. But there are certainly things that it can do really well. But there are also other AI models which are specifically designed to solve problems. Such as the Google's DeepMind. Just last year, actually, DeepMind was able to solve several of these International Mathematics Olympiad problems and even performed as well as a silver medalist would. But still, if you actually focus on their solutions, none of the ideas are new. It's able to search extensively, it's able to recognize patterns, it's able to perform lots of computations, examples, and sometimes even formulate proofs. But if you want to have an original idea, AIs are still not there, and I'm not sure if they ever will be. But as I said earlier, we are still in very early stages of AI revolution, and very difficult to speculate how things are going to be. Yes.
Mathematics is often viewed as a complex subject, but it can also be a source of fascination and fun. There are probably many numbers and numerical concepts waiting to be discovered. Let us enjoy the fascinating world of mathematics and numbers and discover how they can be a rich source of entertainment and enjoyment. Mathematics can and has been the source of entertainment and enjoyment than mere solving of equations and proving theorems. Hello, Dr. Dixit. We're very happy to have you in our studios at Akashvani.
Hi, and nice to meet you.
To begin with, do you think there is still potential areas of mathematics which are waiting to be discovered? So what is your opinion on it?
Certainly. So there are several mathematical problems which are still to be solved. Lots of problems are being solved every year, every day in fact. And as we are moving ahead, we also see lots of new subjects in mathematics being discovered. So if you ask, to give you a simple example, in certain subjects such as number theory, which is my area of expertise, there are some problems which are deceptively easy to state. And there are some other areas where even trying to state the central problems in those areas would be would require a lot of language, lot of training just to understand what the question is. But the most important problems, most coveted problems of today's age are the Millennium Prize problems, which includes the Riemann hypothesis, the Birch and Swinnerton-Dyer conjecture, P versus NP, Navier-Stokes equation, etc., etc. But there are some problems. For example, I can give you an example of a problem which is very easy to state, which in fact I am thinking about right now. And this is a question on which is called the no 3 inline problem. It's not one of the very well-known problems, but it's an interesting problem and we still don't know the answer to it. So the question is as follows. Suppose you take a 4x4 grid and you are trying to find the maximum number of points there such that no 3 points are collinear. Now you can do it by hand and you can construct 8 points which such that no 3 of them are collinear. Now ask this question for a general, n cross n grid, like 1000 cross 1000 or a 5000 cross 5000 grid. And we don't know whether we can always, in a 1000 cross 1000 grid, whether we can always find 2000 points such that no 3 of them are collinear. Or in a n cross n grid, whether we can find 2 times n points such that no 3 of them are collinear. Now, the conjecture or the prediction is that if we take a very large n, then we should not be able to find 2 times n points such that no 3 of them are collinear. That's the conjecture. But we still have no idea what the actual answer is. And many people such as Erdish and others have tried working on it and it is still open. But this is a particular case of a deeper conjecture which falls in the area of Diophantine geometry, namely the Manin's conjecture. But just this particular case is still not known. So this is to give you an example. There are several such problems which needs to be discovered and once needs to be solved. And once you start working on a problem, once you spend a lot of time, even if you are not able to solve it fully, you will be able to solve something, able to find something, and that's still worth it.
I could see that vividly. So just that we spoke about technology and other things. We right now have, in those days, we had only multiplication table books wherein we had to memorize things, but we have technology for everything these days. So do you think students can use technology in a better way to learn and excel math especially?
Oh, absolutely. I think technology plays a very important role these days. And students, as you will see from a very young age, they know how to use computers much better than we were in their age. But it comes with its own dangers. However, if it is channeled correctly, then of course technology is an extremely useful tool, and not just for students. I mean, even for professional mathematicians. Often enough, we use computers to verify conjectures or even to make certain predictions at times. So it's not just that students are the ones who are benefiting from this technological revolution that we have so far. But having said that, there is one danger that I immediately see is students not knowing how to perform basic operations. So just because, there is a calculator can multiply large numbers for you, so I don't even need to know how to multiply. Now that's a danger. You need to know how it is done and then use technology to make it work faster. Go through things which you will take a long time to get by. So that's one of the main dangers of technology, and we have experienced that while teaching undergraduate students at times when they say, why do I need to know how this is, how to calculate something when I can just use my calculator to do it. That's a bit of a risk because then your understanding is no longer as good as it is. Yeah. But technology is absolutely brilliant. We can use it to do a lot of things which otherwise we couldn't. Yes.
Yeah, I could see that teachers care. Okay. What is the future of mathematics when we have app for everything these days? Would students even feel the need to learn or excel in maths?
Absolutely. So there is no alternative in fact. So apps can only search and tell you a few things, perhaps even solutions to standard problems. But as a civilization, if we wish to grow, if we will need a constant influx of new ideas. Mathematics as a subject, it opens up new dimensions and gives us new perspective in whatever you are doing in life. So only through mathematics do various subjects and a priori unrelated topics can be put into one framework and perhaps can also be improved upon. So it's not just a tool. One should think of mathematics as an ultimate testament of human intellect. So going forward, if we really want to distinguish humans from machines, then mathematics has to play a central role in it. Having said that, students can certainly use many of these applications, as you correctly pointed out, towards their better understanding. For example, I have recently learnt of this application called GeoGebra, which gives you a geometric representation of various algebraic things, and probably this is being used in schools. And this was not there in our times, but it's being used now, and it is certainly useful, making their understanding clearer.
Probably it enhances what you
their
try
understanding.
to understand, right?
Absolutely, yes.
So is there any interesting or most surprising discovery that you've come across?
Yeah, so there are several of them that we come across every year or every month or so on. But the most recent one that I can explain to anybody is something that I heard about recently in one of the conferences that I was attending in Japan. And this is as follows. So this is about a real number, which is given as follows. Now, there exists such real numbers, let's say a, such that if I look at a to the 3 to the n and look at the greatest integer which is less than this, which is called the greatest integer function of a to the 3 to the n, I want this to be a prime number for all n. Okay, so a to the 3 to the 1, a to the 3 to the 2, etc. They should all be, and I consider the greatest integer, and they should all be prime numbers. Now, there exists such a's. And once you know the existence of such a's, you can consider the smallest a for which this happens. And the smallest a turns out to be 1.3 something. This is called the Mills constant. And only recently I found out that Mills constant, it has been proved that it's an irrational number and it is expected to be a transcendental number. And I found it really fascinating that such a simple worded problem. And we have some understanding about it.
Okay. So this is like away from what we were just speaking. Every day probably there's maths in a way or the other. So we don't at most times realize that this is because this is the consequence of mathematics. So can you help us identify, for a layman and person like me, can you help us identify what are all the everyday activities which is part of mathematics?
Absolutely, yeah. So, I mean, just look at the things around you. You go to the market, you buy some things, you pay via Google Pay. How do you know it's secure? It uses encryptions or, some cryptography, which is a part of mathematics. Now, we walk in, I'm talking on the speaker, it's using certain transmissions, which is nothing but Fourier analysis, part of mathematics. And even more naively, when the room that we are sitting in, there is a certain structure to it. I mean, this is also mathematics. Pythagoras theorem would be there everywhere that you look around. So starting from very basic mathematics to very deep mathematics, it's there in your everyday life. There is no escape from that.
So how beautiful is math when it intersects with fields like art, music?
Yeah, so there is often comparison made between mathematics and arts. In fact, in various universities, the degree of mathematics is a MA, master in MA in mathematics.
Okay.
Yeah. So it's some places, of course, have it as MSc, but it's also considered a part of art. And it has been constant debate whether one should consider mathematics as a science or an art. See, art, because as I was telling you before, there is an aesthetic aspect to it, to mathematics. And now your question was when mathematics intersects with arts. So I'll tell you certain very interesting things. So there are mathematicians these days, in fact I know some of them, who are composing music using mathematics, using not some very elementary mathematics, but using like really deep mathematics, very deep theorems in algebraic geometry. They are trying to construct music out of it. So that's happening. And also, if you think about art is also in a way appreciating symmetries and patterns and proportions. And mathematics in a way is also doing that, but at a more abstract level. So of course there is a similarity in that.
I think it will be redundant for us to even talk about mathematics as a separate subject. It's the basic of any thinking probably. Okay, I have a very personal question. So what is the life of a mathematician? Do you always think only about numbers?
So I don't know about other mathematicians. I can tell you about my life in general. So doing mathematics involves multiple steps. First is we have to spend a lot of time in studying. You have to keep studying, and then, as I was saying, you need to reflect. You have to keep reflecting, and you have to engage in discussions. And then you have presentations. So these are basically the 4 things that we have to do. Now, reflections can happen on papers, or it could happen while doing other activities. And all these things like studying, reflecting, discussing, and presentations, of course, has to happen in front of an audience. But other than that, all the other things can happen anywhere. It doesn't necessarily happen in our offices. So some of us, you can say, have been working all the time, but it does not mean that we don't do any other fun activities. We do it, but every now and then we go back to it and we keep discussing certain things which interests us. And thinking about problems and thinking about ideas all the time, it also builds you as a person. I mean, there are many times we notice people outside academia, certain problems in life, the way they tackle it and the way we tackle it, there is a lot of difference in it. So it sort of builds you. Your reasoning becomes a little bit better.
More perfection.
No, but you can identify what is important, what is not so important. Those type of things, sometimes when your habit mind takes over, it becomes difficult to distinguish between them. But if you are constantly thinking about ideas, dissecting them, and trying to come up with new creative solutions to things, perhaps it also has some effect on building yourself as a human being as well. Yeah. So
to put it jokingly, probably you can prove everything is right. So thank you so much, sir. Even I had that feeling, yes, mathematicians are serious, but this interview is so much fun talking to you, as much as mathematics itself is fun. Thank you so much.
Yeah, thanks a lot for having me. It was also a lot of fun just talking with you.
Thank you.
All the best. Yes,
thank you. That was the concluding part of the interview, Mathemagic, the Theory of Curiosity, with Dr. Anup Dixit, Assistant Professor, the Institute of Mathematical Science, Chennai. This is Rajarajeshwari signing off and bidding goodbye to all our listeners. This program came to you from the studios of Akashvani, Chennai.